In the following video, we're going to build up what's called our limit toolbox. Last video, we saw that direct substitution was a good technique to use in a lot of cases. With direct substitution, it will always work unless we get an indeterminate form, something like 0 over 0, plus or minus infinity over plus or minus infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, infinity to the 0, or 0 times infinity. For example, let's look at the limit as x goes to 1 of x squared minus 1 over x plus 2. If we try direct substitution on this problem, plugging in 1 for x, we end up with 1 squared minus 1 over 1 plus 2, which gives me 0 over 3, which is not an indeterminate form. It's equal to 0. Therefore, we're done. As another example, let's look at the limit as x goes to 1 of 2 over x minus 1. If we try direct substitution in this case, we end up with 2 over 0. Now 2 over 0 is not defined, but it's also not one of our indeterminate forms. Therefore, we write that this limit does not exist. We will see in a later video that this limit actually is going to positive or negative infinity. For another example, let's look at the limit as x goes to 1 of x squared minus 1 over x minus 1. Again, we try direct substitution, and we get 1 squared minus 1 over 1 minus 1, which is 0 over 0. Notice that this is one of our indeterminate forms. Therefore, we're going to need to use another tool before we can stop and say we have an answer. So now let's start finding some other techniques. We'll start with a theorem. If f of x equals g of x everywhere near x equals c, except possibly at x equals c, then the limit as x goes to c of f of x equals the limit as x goes to c of g of x. Before you worry too much about what that theorem says, let's actually see what it does for us in the problem that we saw in the previous slide. The limit as x goes to 1 of x squared minus 1 over x minus 1. We saw already that direct substitution gave us 0 over 0, which is an indeterminate form. Notice, however, that f of x equals x squared minus 1 over x minus 1 can be factored into x plus 1 times x minus 1 divided by x minus 1. And the good thing about this is that if we let g of x equal x plus 1, that's the same thing as our function f of x, except f of x was not defined at x equals 1, and g of x is. F of x equals g of x everywhere except at x equals 1. F of 1 does not exist, and g of 1 equals 2. By our theorem above, the limit as x goes to 1 of x squared minus 1 over x minus 1 must equal the limit as x goes to 1 of x plus 1, because these two functions agree everywhere except possibly at c. Therefore, we can do direct substitution in the function x plus 1. We end up with 1 plus 1, or 2. So going back to our limit toolbox, we've already seen that we have direct substitution, which always works unless we have one of our many indeterminate forms. It's a good idea to have all these indeterminate forms memorized. It shouldn't be too much work to get them down, especially if you use flashcards. And we've just added a new tool to our toolbox called factoring and/or simplifying. Let's look at some more examples of this. Let's look at the limit as x goes to 5 of x squared minus 25 over x squared minus 7x plus 10. Using direct substitution, we end up with 0 over 0, which is an indeterminate form. But notice that we can factor the numerator into x minus 5 times x plus 5, and we can factor the denominator into x minus 5 times x minus 2. So we can cancel the x minus 5's from the top and the bottom and try direct substitution over again. In this case, if I do direct substitution, I get 5 plus 5 over 5 minus 2, which is 10/3. And that's our final answer. Let's try another example. Let's look at the limit as x goes to 1 of 1 over x minus 1, all divided by x minus 1. Once again, we start with direct substitution, which in this case gives me 0 over 0, which we know now is an indeterminate form. So let's try to simplify the numerator. I start by finding a common denominator for the numerator, which in this case seems to be x. So I'll have 1 minus x minus x over x, 1 over x minus x over x, all divided by x minus 1. Now I combine the numerator into one fraction, so I have the limit as x goes to 1 of 1 minus x over x, all divided by x minus 1. I want to get the x minus 1 out of the bottom, so what I'm going to do is I'm going to multiply the top and the bottom by 1 over x minus 1. So that'll cancel the x minus 1 out of the bottom. Now I'm left with the limit as x goes to 1 of 1 minus x over x times x minus 1. Notice that I can factor a negative sign out of the numerator to get negative x minus 1 divided by x times x minus 1. And now again we can use the factoring and simplifying to get rid of the x minus 1 from the top and the bottom. And I'm left with direct substitution giving me negative 1 in the numerator, and when I plug in x going to 1 in the bottom, I get 1. So the whole thing goes to negative 1. Let's look at another example. The limit as x goes to 1 of the square root of x plus 3 minus 2, all divided by x minus 1. If we try direct substitution, I end up with 0 over 0, which we now know is one of our indeterminate forms. We can't factor or simplify this easily, so we need something else in order to help us solve this limit. So we have a new technique called multiplying by the conjugate. In case you haven't seen it before, the conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. So the conjugate mainly involves changing the sign that appears in the middle. In this case, the limit as x goes to 1 of the square root of x plus 3 minus 2 over x minus 1, we're going to take the conjugate of the numerator. And the middle sign is going to be the negative sign between the square root and the 2. So I'm going to multiply by the square root of x plus 3 plus 2. And notice that I need to do that on the top and the bottom, or else I would dramatically change the function itself. Instead, I've only multiplied by 1. Now let's FOIL out the numerator. So I get the limit as x goes to 1 of x plus 3 minus 2 times the square root of x plus 3 plus 2 times the square root of x plus 3 minus 4, all divided by x minus 1 times the square root of x plus 3 plus 2. Notice that we did not FOIL out the denominator. This is an important tip to help save us time. When we simplify the numerator, we see that the negative 2 times the square root of x plus 3 and the positive 2 times the square root of x plus 3 cancel out. So we're left with the limit as x goes to 1 of x minus 1 divided by x minus 1 times the square root of x plus 3 plus 2. Notice that the x minus 1 cancels from the top and the bottom, and now doing direct substitution we get 1 over the square root of 1 plus 3 plus 2, which is 1 over the square root of 4 plus 2, or 1/4. So going back to our limit toolbox, we have direct substitution, which always works unless we have one of our indeterminate forms. We have factoring and simplifying. And now we have multiplying by the conjugate. And the good news is that almost every limit problem we give you in this class can be solved by any of these three methods. But we are going to every once in a while run into something that cannot. And then for this, we use what's called the squeeze theorem. The squeeze theorem says if f of x is less than or equal to h of x, and that's less than or equal to g of x, and if the limit as x goes to c of f is L, and the limit as x goes to c of g is L, then the limit as x goes to c of h is L. Let's look at a picture to see what this theorem is saying. So in this picture here, I have my upper function in red, which is g of x. Notice that it's always greater than h and f. I have my lower function in green, which is f of x. Notice that it's always below the other two functions. I also have L, which is the limit that both g and f are going to as x gets closer and closer to c. So g and f are pinching together at x equals c. Notice that no matter what h of x does, it's being forced to go to c when x, or it's being forced to go to L when x is going to c. That's what the squeeze theorem says. It squeezes the middle function and forces the y value to be L. Let's look at an example of the squeeze theorem. We have the limit as x goes to 0 of x squared times sine of 1 over x. Now normally we would do direct substitution, but we can't plug x equals 0 into this because of the sine of 1 over x. We note, however, that negative 1 is less than or equal to sine of theta, which is less than or equal to 1, where theta can be any angle in the world. So instead of theta, we can replace it with 1 over x. So negative 1 is less than or equal to 1 over x, which is less than or equal to 1. Now we can multiply all sides of this inequality by x squared, which it's important to note is greater than or equal to 0, so we don't have to worry about flipping the inequalities. When we do this, I get negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to positive x squared. Notice that the middle guy is actually the function that we're hoping to take the limit of. Now, to use the squeeze theorem, I'm going to take the limit as x goes to 0 of the bottom function, which we see then goes to 0, and I'm going to take the limit as x goes to 0 of the top function, which again we see goes to 0. So since the top and the bottom function are both going to 0, that forces the middle function to also go to 0. This is how we use the squeeze theorem. So, going back to our limit toolbox, we always use direct substitution first because it almost always works unless we get one of our indeterminate forms. If direct substitution doesn't work, we do factoring and simplifying or multiplication by the conjugate. In very rare cases, we may need to use the squeeze theorem like we just saw. And in even rarer cases, when even the squeeze theorem won't work for us, we use the technique that we learned in the first video on plugging in values close to c and just estimating what the y value is. This unfortunately only gives us an estimate though. Later in the semester we'll learn one final technique, which is called L'Hopital's rule, which helps us take care of any other cases.